Thanks for watching my video today. Let's discuss what we call a Leibnitz rule. Okay, Leibnitz rule. Okay, here is the statement: if f of x comma alpha, then is our function f is two variables. Okay, that depend on x and alpha, and del f of x comma alpha and upon del x be a continuous function of x and alpha. Then so that d by d alpha of integral from a to b f of x comma alpha dx is equal to integral from a to b the partial derivative. Okay, this is ordinary derivative and this is the partial derivative, meaning when this ordinary derivative or differentiation come inside this or integral, then it will change to partial differentiation. Okay, partial derivative where a and b are independent of alpha. Okay, so then is upper and lower limit. Okay, where we treated alpha as a constant or something like that. Okay, let's get started. Now let our integral from a to b f of x comma alpha dx is equal to capital F of alpha. Okay, we name it. This integral is alpha. Okay, so equation 1, let's say now f of alpha plus this is del. Okay, del alpha is equal to, this is what we call delta, right? Del alpha, which is equal to here. If you replace alpha by alpha plus del alpha, then you get integral from a to b f of x comma alpha by alpha plus del alpha dx, right? And then implies that now subtract them and divide by del alpha. Okay, f of alpha plus del alpha minus f of alpha upon del alpha is equal to integral from a to b integral, same thing. Okay, f of x comma alpha plus del alpha minus f of x comma alpha upon del alpha dx. Okay, now taking limit, okay, both sides. So as limit del alpha tends to 0, that means the denominator. Okay, limit del alpha tends to 0, f of alpha plus del alpha minus f of alpha upon del alpha, which is equal to limit del alpha tends to 0 integral from a to b f of x comma alpha plus del alpha minus f of x comma alpha upon del alpha dx. Okay, so limit del alpha tends to 0, f of alpha plus del alpha minus f of alpha upon del alpha is equal to, taking this limit inside here, right? Because this limit does not depend on this x, so it can go inside or come in outside. Okay, so integral from a to b limit of del alpha tends to 0 of f of x comma alpha plus del alpha minus f of x comma alpha upon del alpha. Okay, now if you see the definition of all derivative, okay, then you get what? Limit h tends to 0, f of x plus h minus f of x upon h is equal to, well, this h is nothing but the increment. Okay, it's nothing but increment. Increment means small increase. Okay, only increasing just a small part only. Okay, so this limit is what we call all derivative. Okay, differentiation. So then is d by dx of f of x. Okay, and again, by definition of the partial derivative that we have already done, we know that limit delta y. Okay, delta y this will be tends to 0. Okay, delta y tends to 0. There here also delta y is nothing but the increment, then is small amount, increase in small amount. Okay, of f of x comma y plus delta y minus f of x comma y upon delta y is equal to the partial derivative del by del y of f of x comma y. Okay, so these two are the definition of or derivative and partial derivative. Therefore, what do we get? So coming back from here, applying this to, okay, so this limit is nothing but same here. Here h is nothing but del alpha. Okay, so you get what? D by d alpha, right? d by d alpha of f of alpha, which is called integral from a to b, and this is nothing but here this one. Here delta y is nothing but del alpha. Okay, therefore you get del by del alpha of f of x comma alpha dx. Now from equation 1, so from equation 1 the beginning here, nothing but f of alpha is nothing but this one, or integral. Therefore d by d alpha of integral from a to b f of x comma alpha dx is integral from a to b the partial derivative of f of x comma alpha with respect to alpha, okay, into dx and dx. So this is what we call the Leibniz rule in Leibniz rule. Okay, that's it.